Hey, welcome back to my Project Euler series in Python. This is problem 5. Smallest multiple. 2520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. So what is the smallest positive number that is evenly divisible by all of the numbers from 1 to 20? Okay, so how can we do this? So if 1 to 10, if it can be evenly divided by each of the numbers from 1 to 10, then that means it's the lowest common multiple of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, let's do some rough working here. So if we just print 1, 2 times 3 times 4 times 5 times 6 times 10. Okay, so this is that. So that number is also divisible by all of the numbers from 1 to 10. But yeah, it's not the smallest. So how do we find the lowest common multiple of all of those numbers? Well, I guess we could break them into their prime factors, right? So let's think about problem 3 again. So if we have their prime factors, then because every number is either prime or a product of primes, then the lowest common multiple will just be the product of all of the prime factors that aren't duplicates, if that makes sense. So let's illustrate that from 1 to 10, for example. So you got 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 2 is 2, 3 is 3, 4 is 2 and 2, 5 is 5, 6 is 2 and 3, 7 is 7, 8 is 2 and 2 and 2, 9 is 3 and 3, and 10 is 2 and 5. So if we take all the prime factors without repeats, then let's see what we get. So when I say without repeats, I mean repeats in between the values. So let's just see what that would look like. So let's start with 2. So we need 2, then 3 we need 3, then 4 we need 2 and 2. But as you can see, we've already got 1, 2 here. So if we just take another 2, and 5 we need 5, 6 we need 2 and 3. Well, we've already got 2 and 3, so we don't need anything more. 7 we need 7, 8 we need 3 2's, so we got 1, 2, so we just need 1 more. And 9 we need 2 3's, so that's 1 more. And 10 we need a 2 and a 5, which we've already got. So hopefully that made sense, and hopefully also the product of this is our example solved, in which case we can work on building the logic for the numbers 1 to 20. Excuse my mistyping here. There's got to be a faster way to do this, but anyway. So that is sweet. Yeah, so that's the number from the question. That's the smallest number that can be divided by each of the numbers 1 to 10 without any remainder. So we figured out how to find the lowest common multiple. So what did I actually do to get all of these numbers? It was obvious really, but what I'm trying to say is, how do I tell the computer to do that? So I need to firstly get the prime factors for each of the numbers from 2 to 10, or in the case of the question, to 20. But let's see if we can automate this example first, and then it should be a matter of replacing the 10 with a 20. So we need to get the prime factors for each of these and then compare it to what we have as we go along, accumulating them. And if there's a number missing, then that's what we want to add to our list. And then once we've got all of that, it's just a matter of multiplying whatever's in the list together at the end. Okay, let's go with that then. Let's see if we can do this. So for I in range 2 to 10, which basically means I have to write 11 there, because if you remember from the last example, it's non-inclusive. So this should give us the numbers 2 to 10, inclusive, and we want to basically say, give us the factors. So factors is equal to, and then we want some function that's going to do that for us. And if you remember from problem 3, this worked pretty well to give us prime factors. Sorry, that's problem 4. So let's do this. Def, I don't know, prime factors, and it should take the number that we want to get the prime factors for, so let's call that n, and let's indent that so it's all in the function. We also need a colon for the definition, and pulling in the normal square root function. Factors is other prime factors that we're going to need. Shadowing it. Let's just call this p underscore factors. And yes, I'm using snake case. I think it's more, what's the word? It's more common to use snake case in Python. It's not like camel case, which is mainly seen, I don't know, in Java or more object-oriented programming. I don't know. It's just a preference, but I prefer snake case for Python. Of course, it makes sense as well because Python's a snake. But anyway, so let's see. So this should work straight out the box from problem 3. So if we just return the list of factors that we get, then we can sort of see how this goes. So if we just say prime factors I, and then let's print p factors, my bad, p factors, then hopefully it should give us the list that replicates what this looks like. And I believe that is correct. That worked relatively well. So now we need the logic regarding how to come up with this list. So like I said before, we go through and we add things to the list incrementally, only what's missing from the list. So if everything in this list is already in this list, we don't need to add anything. So how can we do that? Well, firstly, we need to figure out what is in each list. So let's get the total factors, which we can set as an empty array. So that's going to be this guy that we're aiming to populate. So it's going to start off empty. Then, based on the current amount of each number in this p factors list, whatever's missing from total factors we want to add. So I think there's this cool function called counter. Let's see if I can import this. It's from collections, counter. So if we do counter and then p factors, let's see what that does. Oh great, I've got to print it. That didn't show us a lot. So what the counter stores is the list. It stores a dictionary of the values in the list and the number of times that value occurs in the list. So if we're trying to get the prime factors of 2, obviously it's just 2. So the 2 occurs once. Similarly for 3, and then when you get to 4, the 2 occurs twice. And so you can see it quite easily and quite clearly matches up with the list that it's relevant to. It's just showing the number of occurrences of each element in the list. So now how can we use counter? So we can basically say if it's not in, if the count of a certain element is, well, any element is less than the count that we already have in here, then we just want to add that on to the original total factors. So let's see if we can do some magic on that. So if the individual factors minus the counter of the total factors is, so if this thing is going to give us the difference, right? So if we print this, I mean it's just gonna print the same thing because we're not doing anything with total factors at the moment. So let's see, what can we add? Well, we should be able to just add what this thing is, right? Whatever this counter comes up as. So if we do this thing, I think it's that and then dot elements. So the difference of two counters should be another counter. And if we do dot elements, then it should just give us the elements that would be in the original list. So for example, if the counter says 2, 3, then it's just gonna, the dot elements is just gonna be that, I think. Let's see. Let's just see. Okay, that's clearly not nice. Maybe if we have to cast it back to a list. Cast the whole thing back with the elements maybe. Okay, sweet. Okay, so we've basically just printed the list minus an empty list. So that's not great, but what we can start to do is populate that total factors list. Instead of printing this, if we do total factors dot append, then we'll be adding on whatever we've got in here in our individual guy minus everything that we have already, which in turn will just be adding those extra elements, which in turn should accumulate this list. So if I print total factors, it'd be amazing if this works first time. And there it is. Dot append. I don't think we can append on a list. What we could do is merge the lists. Would that work? Maybe they don't need to be in a bracket. So parentheses. Wow. Okay. That worked perfectly. Nice. Okay, that's the exact list we wanted. So total factors ends up being the list of the primes that we need. So all we need to do now is multiply them all together. So if we do for I in total factors, apologies for using I everywhere, but it's just easier, I think, and there's no scope clashing really. Okay, maybe there is a little bit, but we can make our peace with that because we know how scopes work. So we don't want to print I. We want some kind of total. So let's figure out, let's call it lowest LCM equals 1. LCM for lowest common multiple. So it's going to be LCM times equals I, and then print LCM. And there you go. So that gives us the product of what was in the list. Sweet. Okay, I guess that's the original example taken care of. So we should be able to just change to 20 and it should work straight away. Let's give this a go. Like I say, it's non-inclusive, so we have to go 21, but it should be to 20. And okay, So yeah, there we have up to 10, and then the only things missing after that are 11, 13, 17 and 19, which are the primes, and then an extra 2 because 16 is 2 to the 4, so we need a fourth 2 in there. But as you can see, 12 is taken care of by 2, 2 and 3, and 14 is taken care of by 2 and 7, 15 is taken care of by 3 and 5, 16, there we go, we needed the extra 2, 17, 18 was the 2 3s from the 9 and then one of the 2s, 19 is prime, and 20 is just 2, 2 and 5. So everything's taken care of already in there, mainly from up to 10, other than the primes greater than that and the extra 2. And this is our product, our lowest common multiple. So no need to print the factors, and then the program should just be correct. So let me show you the whole thing. So we've got our prime factor code here. Okay, maybe the program likes it there. And so this gives us the prime factors. Then we go through, and all the magic is really happening in here. We're taking the number of elements that we have in each individual, so we create the counter dictionary for each of the prime factor lists that we get for each number from 1 to 20, and we say what's missing from here, what's missing from here in the current list of total factors, and then and that's calculated by the subtraction. We then get the list of those elements and merge it into the total factored list. So I'm pretty confident that this is the right answer then, because it worked for 10. So let's just sign in and double check. 4, 1, 3, 6, 5, and smallest multiple. Boom. Yeah, like I said, I solved this before, so unfortunately we don't get to type the answers in, but yeah, we know we got it right, and kind of focusing on the methodology, because if, say, this was in an interview and you'd done the original method of going through by hand and doing them 1 to 10, and then they said, okay, now do it for 20, then you'd be there and you'd be like, oh, okay, well, I only have to, calculate 11, 13, 17, 19, and add the 2 on for the 16. And that would give me the lowest common multiple based on the prime factors. But then say the interviewer goes, oh yeah, actually, no, we didn't mean to put 20 here, we meant to put 100. Then you'll be like, oh, what? And you'll be sat there for ages, whereas now we can just do this. 101, run, and boom. We've got this thing. Let's see how far I'll go. Maybe 1,000 is a bit of a stretch. No, wow, that was so fast. Okay, that's a large number. So yeah, as you can see, you would struggle a lot to do that by hand, but the program that we've written is very easily adaptable to stretch. All right, I imagine somebody's curious to see if 10,000 would even work. Oh wow, that was quite quick though, and we'll be scrolling all the way there. So yeah, I'll leave it as 20 for now because that's the question, but that's just my style of programming. I like to somewhat future-proof it. Anyway, that's problem 4. That's problem 5. I will see you on problem 6. Thank you.